Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC702C. Topic Gunn diode. Gunn effect. In 1963, J.B. Gunn observed a periodic variation of current passing through an N-type gallium arsenide semiconductor. He found the following: when a DC bias voltage is applied to the contacts of N-type gallium arsenide or indium phosphide. These are: the current first rises linearly from zero, then it begins to oscillate when a certain threshold is reached. The time period of oscillation is equal to the travel time of electrons from the cathode to anode. This is known as Gunn effect or bulk effect. Gunn effect. From Gunn's observations, the carrier drift velocity is linearly increased from 0 to a maximum value when the electric field is varied from 0 to a threshold value. When the electric field is beyond the threshold value of 3 kV per centimeter for the N-type gallium arsenide, the drift velocity is decreased and the diode exhibits negative resistance. This situation is shown in figure. That is, when the applied electric field reaches at 3 kV per centimeter, the drift velocity starts decreasing from this point. Gunn diode, generating microwave signals anywhere from around 1 gigahertz up to frequency of possibly around 100 gigahertz. Gunn diodes are also known as transferred electron devices. Although it is referred to as a diode, the device does not possess a p-n junction. Instead, the device uses an effect known as the Gunn effect. The Gunn diodes are easy to use. They form a relatively low-cost method for generating microwave RF signals, often being mounted within a waveguide to form a simple resonant cavity. Gunn diode construction. Gunn diodes are fabricated from a single piece of N-type semiconductor. The most common materials are gallium arsenide and indium phosphide. However, other materials including germanium, cadmium telluride, indium arsenide, indium antimonide, zinc selenide, and others have been used. Among the three layers, top layer, middle layer, bottom layer, the topmost and the bottommost are heavily doped, while the middle layer is lightly doped. The middle layer is also called active layer or active region. The middle layer is an epitaxial layer grown on the N-type substrate, and the topmost layer is formed by ion implantation technique. The active region is between a few microns and a few 100 micron thick. This active layer has a doping level between 10 power 14 per centimeter cube and 10 power 16 per centimeter cube. Gunn structure. Symbol of Gunn diode. Gunn effect can be explained on the basis of domain formation, two-value model theory, or RWH theory. VI characteristics of Gunn diode. The current in Gunn diode starts increasing initially in the applied DC voltage. At a particular point, the current starts decreasing. This point is called threshold point or peak point. That is, when the applied voltage is increased from 0 up to some threshold value, the current will increase, and after crossing the threshold point, the current starts decreasing, and this creates negative resistance region in the diode. This is the position of a negative resistance region. Due to this negative resistance region, the diode acts as amplifier and oscillator. Advantages of Gunn diode: portable and small size device. The cost of manufacturing of Gunn diode is low. It possesses better noise to signal ratio as it is immune to noise disturbance. The Gunn diode is reliable and stable at high frequencies. It has a high bandwidth of operation. Disadvantages: the Gunn diode has poor temperature stability. The device operating current is higher and therefore power dissipation is more. The efficiency of Gunn diode is low, below 10 GHz. Applications of Gunn diode. Gunn diodes are used as oscillators and amplifiers. They are used in radio communication, military and commercial radar sources, used in fast controlling equipment, in microelectronics for modulation of laser beams. It is used in tachometers. Gunn diode is used in sensors for detection, in trespass detecting system, in door opening system, pedestrian safety systems, etc. It is also used extensively in microwave relay data link transmitters, RWH theory. The differential negative resistance formed between a third fifth group compound is shown in figure. You can observe the negative resistance behavior. That is, as the electric field increases, the conduction current decreases from this point. This is the position of negative resistance region. The next is two-valley model theory. When some electric field is applied, the electrons will move from the valency band to the lower valley of conduction band. Now here, if we observe the mobility of the electrons, uh, the conduction current starts increasing up to certain point, and after reaching certain point, if the applied electric field is above the lower valley and greater than the upper valley, this is the position of lower valley, this is the position of upper valley. Now this is the applied voltage, then the transfer of electron takes place from lower valley to upper valley. Here you can observe the decrease in electron mobility, and in this region the current starts decreasing. Just now I explained the movement of electrons from lower valley to upper valley. The transfer is taking place. This is the situation if the applied electric field is above the level of upper valley. All the electrons are transferred to the upper valley, and here you can observe the negative resistance region when the electron transfer takes place from lower valley to upper valley. In this region, the negative resistance, the device behaves negative resistance. Here, when the electrons move from lower valley of conduction band to the upper valley of conduction band, the electron mobility decreases. That will in turn reduce the conductivity. Thank you. We will meet with the next lecture.